Hello ladies and gentlemen, and welcome to Mr. Saucedo's YouTube videos. Today we're going to be going over the combined gas law, so make sure that you're following along in your note packets. Then if you have any questions, you ask tomorrow. So we talked about the three different types of gas laws out there, and now we need to talk about what we call the combined gas law. And so as it appears, the combined gas law is what you get when you combine the three previous gas laws. So when you take Boyle's law, Charles' law, and gay-Lussac's law, you get the combined gas law. This is our equation for the combined gas law, and it is probably one of the most important equations that you'll be seeing in this semester. So P1 times V1 over T1 equals P2 times V2 over T2. All right, now all the ones that you see, so all of these little guys right here, this one, that one, those refer to the initial conditions, so what we are starting with. The 2's, though, those are our final conditions, so that's what the little 2's here represent. And if you ever forget, the way that I always remember this, and it's a life lesson, please vomit over the toilet. So that's the way that I always remember PV over T. So PV over T, please vomit over the toilet. So what are the important points of being able to use PV over T? Well, there are a couple of important things that we need to remember. The first of which is whenever we're using gas laws, we need to be using Kelvin. Okay, so we need to use Kelvin as our temperature unit whenever we are doing gas law problems. Now, the reason why makes a lot of sense. Dividing by 0, you can't do that. So if you have 7 divided by 0, your calculator will explode. It won't give you an answer. It'll say undefined. Why? Because there are an infinite number of answers to that question. So there isn't really a direct answer when you divide by 0. Okay, and so we have to use Kelvin because as far as we know, we can never reach absolute 0. So at least we'll never divide by 0 if we use Kelvin. Also, much like the three gas laws, if a variable is held constant, then it can be ignored from the equation. So here's the question. If a problem only mentions pressure and volume, or if it says temperature is constant, then, all right, what can we do? So again, if it only mentions these two things, or if it says temperature is constant, then this equation simplifies down to P1 times V1 equals P2 times V2. Now, do you remember whose law that is? That's Boyle's law. All right, so that's Boyle's law, and that's, again, the reason why this sort of equation is all three put together. What if instead it said only volume and temperature and it didn't mention pressure at all? Well, in that case, then pressure would get crossed out, and you'd have Charles' law. And then finally, what if volume was held constant? So if volume was held constant, then I have gay-Lussac's law. So that's the reason why we can use this gas law, the combined gas law, instead of having to remember three separate ones because it involves everything. The very final thing we need to talk about and be aware of is what exactly are standard conditions, because a lot of times when we do gas law problems, it mentions that everything is at a standard condition. So what does that mean? STP, something that we talked about all the way back in Unit 8, standard pressure is 1 atmosphere. Standard temperature is 0 degrees Celsius, but because we're doing gas law problems, we have to use Kelvin. And so that's 273 degrees Kelvin. So again, we abbreviate that as STP. And so sometimes, instead of giving you a pressure and a temperature, it'll say this gas is at standard temperature and pressure. So it's important that you also remember what STP stands for. When are we going to use this gas law? Because there are multiple gas law equations, so when am I going to be using this one? P1 times V1 over T1 equals P2 times V2 over T2. Anytime you are given different pressures, different volumes, or different temperatures, that's when we use this equation. It's extremely useful only if we are changing pressure, or we're changing volume, oops, wrong color, volume, or we're changing temperature. So if we're changing those variables, that's when we use this gas law. So if you don't have a calculator, take one out because we're going to see if we can solve these. This is the way that combined gas law questions look. pretty unassuming. Let's read it first, though. Example, a sample of methane has a volume of 3.8 liters at 5.00 degrees Celsius and is heated to 86.0 degrees Celsius in a container at constant pressure. What would its new volume be? So in every single one of these situations, what we're going to do is kind of what we did with stoichiometry. We're going to underline important pieces of information. So the volume that I have and I'm given is 3.8 liters. I'm given a temperature, 5. I'm given another temperature, 86. And I'm also given the fact that this is at constant pressure. That's extremely important. What am I being asked to find? I'm being asked to find what the new volume of this would be. So in other words, you can pretend like I have a container at 3.8 liters, 5 degrees. If I heat this thing up to 86, what should happen to the volume at constant pressure? Let's write out our formula first of all, though. So I have P1 times V1 over T1 equals P2 times V2 over T2. So a couple of things to point out whenever we start gas law questions. I have to have my temperature in Kelvin. So what is 5.00 degrees Celsius to Kelvin? So in case you forgot, you add 273. So this should actually be 278 K. What about 86? So again, you add 273. That would be 359 K. Those are both important things. So don't forget, never use Celsius. It says it's at a constant pressure. That's also important. So technically, pressure doesn't matter. So all I have is V1 over T1 equals V2 over T2. Now I can plug in all of my stuff. Okay, so let's plug in our values. So what is my first volume? My first volume is 3.8 liters. What is my first temperature? My first temperature, it's at 278 K. What is my final volume? Well, that's what I'm asking for. So that's like my unknown. That's my X. And then on the bottom, I have 359 K. That's my new temperature. So solve for this algebraically. You can rearrange things, you can do whatever you want, but I'll just write this out. So we have 278x equals 3.8 times 359. Yes, you should always keep your units, but I'm just doing this in case you weren't sure how to algebraically solve for that. So my 278s disappear. So when I plug that in my calculator, what do I get? I get 4.9, and I need a unit, liters. That's my volume unit. So 4.9 liters. And does that make sense? So I started here. If I take a look, I wonder if I can do this. Yeah. So I have right here 3.8 liters at 278. I heat that up. What should happen to the volume? The volume should go up, and it does go up. It goes up to 4.9 liters. That makes sense. Let's try another example. So example, a sample of diboron gas has a pressure of 345 torr at a temperature of negative 15.0 degrees Celsius and a volume of 3.48 liters. If conditions are changed so that the temperature is now 36.0 degrees Celsius and the pressure is 468 torr, what will the new volume be? So again, just like before, underline key pieces of information. So I have diboron gas at a pressure of 345 torr, a temperature of negative 15 degrees Celsius, a volume of 3.48 liters. If conditions are changed, so now the temperature is 36 degrees and the pressure is 468 torr, what will the new volume be? That's what I'm being asked to solve for. So we start by writing out our equation. P1 times V1 over T1 equals P2 times V2 over T2. Again, key thing, temperature has to be in Kelvin. So let's solve these for Kelvin. So negative 15 degrees Celsius, I can't have that. All right, that instead is, I'll write a little arrow over here, 258 Kelvin. What about 36 degrees? So 36 degrees, that becomes 309 Kelvin. Now, nothing's held constant, so I'm going to have to plug in all of these things. So let's plug in our values, and we'll see how we do. Okay, so I have pressure 1. What is my starting pressure? 345 torr. Okay, next up, volume 1. My first volume is 3.48 liters. After that, my starting temperature, 258 K. And that equals our new pressure. Our new pressure is 468 torr. I almost miswrote that. New volume, I don't know what that is. That is my X. That is my unknown. And then my new temperature, 309 K. So that's my setup. Now all I need to do is solve for X. So let's see if I can actually solve for X. I don't really have very much room here, but I'll just try to write it as quickly and easily as possible. So my setup for this should be something like this. All right, so I should have 345. Again, make sure you always keep track of your units. I'm just doing this so that it actually, saves some space. 309, and it'd be divided by 258, 468, and that would give me my X. So this is what X would equal. So plug that into your calculator and see what you get. When you plug that in, you get about, let's see, X equals 3.07. And then if I'm following my units, that should be liters. And that is what the answer to this question would be. Let's try one last example. So a container has a pressure of 17 atmospheres and is kept at 32 degrees Celsius. What would the pressure be now at 100 degrees Celsius? All right, so again, let's start with underlining important pieces of information. 17 atmospheres, 32 degrees Celsius. What would the pressure be? That's what I'm looking for. What would the pressure be at 100 degrees Celsius? So what I need to do again, first thing, make sure that I have all of my units correct here for temperature. And so 32 degrees Celsius, that's not going to work. That needs to be 305 K. 100 degrees Celsius, that's not going to work. It needs to be 373 K. Now I write out my equation. P1 times V1 over T1 equals P2 V2 over T2. Now, what am I missing here? Well, volume isn't mentioned at all. And so since volume isn't mentioned, it's almost as if this is gone. And if that is gone, then all I have here is gay-Lussac's law. We're assuming that our volume is constant. Now I can plug everything that I need in. What's my first pressure? 17 atmospheres. What's my first temperature? 305 K. What's my new pressure? I don't know. What's my new temperature? 373 K. So now let's solve for X. And so again, I'll write that out just for completion purposes. So we have 305 times X equals 17 times 373. Again, keep track of your units. I'm doing this just because I don't have enough space to write out all the units. And so that would cancel out, and that's how you would get X. Solve that by putting that in your calculator, and you get about 20.8 atmospheres. Okay? Now, does that make sense? Let's take a look and see what happens. So if I have 17 atmospheres of pressure, and I have 305 degrees K, if I increase the temperature, what should happen to the pressure? The pressure should go up, and it did. It went up to 20.8 atmospheres, and that makes perfect sense. So that's how you solve combined gas law questions. If you have any problems, make sure you ask tomorrow.